And think about it, the electric car revolution's charging ahead, right? But there's this quiet bottleneck. The batteries. We're aiming for that same freedom and range we had with gasoline, and, well, current battery tech still has some catching up to do. Okay, let's unpack why this is such a hot topic.
What's truly compelling is how this push for better batteries isn't just one field. It's a massive, coordinated effort across engineering, chemistry, materials, science, you name it.
Yeah.
It's about more than just driving further. It's about making these power sources incredibly safe and understanding exactly how they'll behave in, well, every situation imaginable, and predicting their lifespan with pinpoint accuracy.
Absolutely. And that's the heart of our discussion today. We've got a fascinating collection of information here, mainly stemming from a detailed automotive engineering textbook that really dives deep into the world of computer simulations and real-world testing.
Right, a really thorough source.
Yeah. So consider this your fast track to understanding the key challenges and breakthroughs. We're going to explore battery safety, the advanced modeling techniques being used, and what the science tells us about how batteries age over time. Our goal, to pull out the crucial insights about the future of powering our vehicles.
Okay, starting with safety then. If we look at the big picture, the automotive world operates under some of the strictest safety regulations out there.
Definitely.
And when you're dealing with energy storage systems that pack such a punch of power, well, those rules become non-negotiable. Quality and long-term reliability aren't just ideals. They're absolute requirements for something we rely on for transportation every single day.
Got it. I mean, you wouldn't want to think twice about the safety of the battery in your car, especially with passengers. That's where the standard called ISO 26262 comes into play, doesn't it?
It does, yes.
Yeah. It's like a safety blueprint specifically for electrical and electronic systems in vehicles, and it's hugely relevant to what's inside those battery packs. So the key takeaway here is that the automotive industry has a rigorous step-by-step process to identify and mitigate battery safety risks right from the drawing board.
Exactly. ISO 26262 essentially outlines a complete safety journey for a vehicle system, starting with the very first idea and going all the way through design, manufacturing, how it's used, and even what happens when it's no longer needed.
Okay.
A critical stage in this journey is hazard analysis and risk assessment, or HANRA. This is where engineers act like detectives, meticulously trying to identify every potential danger that could arise from the battery system.
So they're trying to think of every single thing that could possibly go wrong. What kind of methods do they use for that kind of deep dive into potential problems?
They employ several well-proven techniques. There's FMEA, which stands for failure mode and effects analysis. It's all about looking at potential ways a component could fail and what the ripple effects of that failure might be. Then you have CONHEM-AA, which focuses specifically on the initial design phase, and HAZAP, or Hazard and Operability Study, which is a more structured brainstorming approach to identify potential hazards and operational issues. Through these methods, they've identified the main safety concerns for battery systems. Think about fire or explosion, the release of dangerous gases like hydrofluoric acid. If there's a leak, high voltage electricity, over 60 volts DC is considered hazardous. And even if the cell's built-in safety release mechanism, the vent, fails.
Wow, that's a pretty sobering list of possibilities. And I recall seeing something about ASIL levels. What are those all about?
Yes, ASIL. It stands for Automotive Safety Integrity Level.
Okay.
It's essentially a way to categorize how critical a particular hazard is. It goes from ASIL A, which is the least critical, all the way up to ASIL D, which is the most critical.
So if something gets an ASIL C rating, what kind of extra precautions or testing might that involve compared to an ASIL A?
Well, the higher the ASIL, the more demanding and costly the development process becomes, because you need to implement more sophisticated and robust measures to address those higher levels of risk. It requires more rigorous design, more testing, more validation.
Okay, so after they've analyzed all the potential hazards, they assign one of these ASIL levels to each one. And that level then dictates how much effort and what types of safety features need to be designed and implemented.
Precisely. Following the assignment of ASIL levels, specific safety goals are defined for each potentially hazardous event. Then comes the functional safety concept, or FSC.
FSC, got it.
This is where the actual safety measures are outlined. These can include electrical and electronic safety features, external measures like emergency procedures, or even other technologies like mechanical safeguards built into the battery itself.
That makes sense. Can you give me some concrete examples of these safety measures, maybe at the level of an individual battery cell?
Absolutely. At the cell level, you might find something called a charge interruption device, or CID. This is a physical component designed to break the electrical connection within the cell if the pressure inside gets too high.
Like a little circuit breaker.
Kind of, yeah, mechanically triggered by pressure. Then there's thermal management systems for cooling and heating the cells to keep them within their safe operating temperature range. Extremely important.
Right.
And finally, vent gas management, where each cell is designed with a specific opening to safely release any gases that might build up inside in case of a problem.
It's interesting that they consider things that aren't electrical right from the start of the design process. Why is that so important?
Well, the key idea behind considering non-electrical measures early on is that if you can incorporate robust mechanical or other non-electronic safety features, you might be able to reduce the required A cell for certain hazards.
Oh, okay.
Think of it like having a backup plan or reducing the reliance solely on the electronics. This can ultimately lead to lower development costs for the complex electronic control systems.
That's a really smart way to think about it, layering the safety measures. The notes mention a specific example involving a PHEV battery. Can you walk us through how they applied these concepts in that case?
Certainly. For this particular PHEV battery, the initial hazard analysis identified potential issues like high voltage, leaks, fire, and the risk of explosion.
Yeah.
Standard stuff.
Yeah.
They then conducted a detailed situation analysis, taking into account how the vehicle might be used, the environment it operates in, even weather conditions, to pinpoint specific scenarios where these hazards could occur. Using ConHEF-EA, they started with, get this, over 600 possible combinations of failures and conditions.
Whoa.
And narrowed it down to 121 that were deemed plausible.
Wow, that's a massive reduction. How did they determine which ones were plausible?
By carefully evaluating the likelihood of each specific combination actually happening. Some failure modes might be extremely unlikely to occur simultaneously with certain operating conditions.
Makes sense.
Then they used risk assessment parameters, things like how severe the potential injury could be, severity, how often the situation might occur, exposure, and how easily the driver or system could prevent harm, controllability, to determine the ASIL for each of those 121 events.
Okay.
And if any of those parameters were basically zero, meaning no potential harm, no possibility of exposure, or complete control over the situation, then only standard quality management or QM procedures were considered necessary. No specific safety development needed for that event.
And for the more serious scenarios, how did they go about figuring out what safety measures to put in place?
Right, so let's take a specific example. Imagine the vehicle is parked and turned off in a garage. They realized that relying solely on electronic safety measures might not be sufficient in this scenario.
Because the car's systems might be off?
Exactly, or partially off. So they considered non-electrical measures, like building the battery pack with a fire-resistant housing. They also looked at external measures, such as having fire detectors and fire extinguishers present in the parking garage itself.
Okay, so they've thought about these safety measures. What happens next in the process? Is it like, check, done?
Not quite. This is where the iterative refinement comes in. They went back and reassessed the risk of each hazardous event after hypothetically implementing these safety measures.
Ah, okay.
For example, that fire-resistant housing could significantly reduce the potential severity of a fire, maybe from something life-threatening down to just light or moderate injuries.
Right.
And having fire detection and extinguishing systems readily available would greatly improve the controllability of the situation.
So by adding these safeguards, the initial ASIL rating for a particular hazard could potentially be lowered?
Exactly. By proactively thinking about and incorporating these non-E measures, they aim to reduce the overall risk that remains and potentially lower the stringency and therefore the cost associated with the required electronic safety systems. However, one interesting challenge they pointed out is figuring out who is responsible for a hazard that's not a direct, immediate consequence of an electrical or electronic system failure. It can be a tricky web of cause and effect sometimes.
That makes a lot of sense. Shifting gears now to another crucial aspect, battery modeling, particularly for what happens in a crash. It sounds like this has become a much bigger focus with the rise of electric vehicles.
Oh, absolutely.
So we've talked about preventing battery failures in general. Now let's look at what happens when the unavoidable occurs a crash and how engineers are using advanced tools to ensure batteries remain safe even in those extreme situations.
Absolutely. With more and more EVs and hybrid vehicles on the road, ensuring battery safety in the event of a crash has become just as important as traditional goals, like increasing battery capacity or making them last longer.
Yeah, you have to assume crashes will happen.
Exactly. And the automotive industry needs reliable and efficient ways to use computer simulations to predict how batteries will deform and potentially fail if a vehicle is in an accident.
It must be incredibly complex to create a computer model that accurately predicts something as chaotic as a crash and how a battery will react. Where do they even begin with something like that?
Well, the approach they suggest involves several key stages. First, they conduct physical crash tests on individual battery cells to really understand their fundamental behavior, how they deform, where they might crack or break under load.
So real physical tests first.
Yes, physical testing is crucial for grounding the models in reality. Then, they take that real-world data and use it to build virtual models of single cells using a technique called finite element analysis, or FEA.
FEA, okay.
These single-cell models are then combined almost like virtual building blocks to create models of larger battery modules and eventually the entire battery pack.
Right.
Finally, these virtual models are validated by comparing their predictions to the results of actual physical crash tests on modules and packs. So it's this cycle of testing, modeling, combining, and then validating again with more tests.
So it's a step-by-step process, starting with the smallest building block and working their way up to the complete system, validating as they go.
Precisely. And FEA is the crucial tool here. It allows engineers to visualize what's happening inside the battery during a simulated crash. Things that would be difficult, if not impossible, to see clearly in a real-world test.
Like seeing inside the pack during impact.
Exactly. The notes even mention an example of a non-standardized EV crash test where FE modeling helped them see exactly how the battery pack under the back seat was deforming during the simulated event.
That sounds incredibly valuable for designing safer vehicles. What kind of specific computer simulation methods are they using for this?
They commonly use explicit FE methods with powerful software tools called solvers, like AbaQuest, LS-DYNA, PAM-Crash, and radios.
Ah, the industry standards.
Yes. These are industry standard in vehicle design for analyzing structural integrity and simulating crashes. These methods allow engineers to handle a wide range of crash scenarios and really speed up the vehicle development process by reducing the need for numerous physical prototypes and tests.
I can imagine that running these detailed crash simulations requires a huge amount of computing power, though. Is there a trade-off between the level of detail and how long these simulations take?
Absolutely. There's always a balance to strike between the level of detail you include in the simulation, what we call the mesh density, and the computational resources required.
Right.
The more detailed the battery model, meaning breaking it down into a finer mesh of virtual elements, the more accurate the predictions are likely to be, but the longer the simulation will take to run. Significantly longer.
And cars already have complex models.
Exactly. While a full vehicle crash model can already involve millions of these elements, adding highly detailed battery models pushes those numbers even higher. It's a major computational challenge.
So they're constantly trying to find that sweet spot between getting accurate results and keeping the simulations practical in terms of time and cost. Now, how do these computer models actually relate to real-world safety ratings for electric vehicles?
Well, currently, the safety ratings for vehicles with high-voltage batteries rely on a combination of government regulations, industry guidelines, and standardized physical crash tests. Things like the FMVSS standards in the US or Euro NCAP.
Okay.
However, these sophisticated FE battery models are becoming increasingly important in predicting how batteries will perform in these tests and in helping manufacturers design batteries that meet and exceed the required safety standards before they build expensive prototypes.
How do they actually describe the physical behavior of the battery's components within these computer models, like the materials?
They use a virtual representation of the battery's geometry broken down into many small elements connected by nodes, much like they would model any other structural part of a vehicle.
Like a digital twin, sort of.
Kind of, yeah. Then they apply material properties based on stress strain curves that they've obtained from those initial physical tests on battery materials. This allows them to simulate how the materials will deform and potentially fail under the immense forces experienced during a crash.
What about the more intricate parts of the battery, like the individual cylindrical cells and the larger modules they're assembled into?
For cylindrical cells, they model components like the aluminum casing that holds everything together. For the larger battery modules, they'll include the outer casing of the module, the electrical conductors that connect the cells, the insulating materials, and the joints or fasteners that hold it all together.
Okay.
One really important aspect here, something mentioned in the notes, is modeling any preload that might be applied to the modules during assembly.
Preload, what's that?
It's an intentional compression force applied to the cells within a module. This is often done to ensure good electrical contact and maintain pressure over the battery's life, but it also significantly influences how the module behaves structurally in a crash. So it needs to be included in the model.
Ah, preload. That's an interesting detail I haven't thought about. And what about the inside of those cylindrical cells? That jelly roll of materials looks incredibly complex.
It is indeed. Modeling the jelly roll accurately is a big challenge.
Yeah.
There are really two main ways they approach it. One is to create very detailed, almost microscopic models, trying to represent the individual layers of anode, cathode, and separator.
Super detailed.
Right. These can help researchers understand the fine-grained deformation behavior. However, these models require a huge amount of computing power and very precise material data for each thin layer, which can be difficult to obtain.
Okay, so what's the other approach?
The other approach is more macroscopic, or homogenized. They treat the entire jelly roll as a more uniform material with effective overall properties, rather than modeling each individual layer. It's an averaging approach.
So those super detailed models are more for fundamental scientific understanding, while the more simplified, homogenized models are more practical for running full vehicle crash simulations.
That's a good way to put it. Generally, yes. Another critical aspect of crash modeling is being able to predict when materials might break or joints might fail.
Yeah, that seems vital.
Absolutely. This is essential for determining if the battery casing could rupture and leak potentially hazardous materials, or if structural supports might give way, changing how the battery itself deforms during the crash. They use specialized models to represent the behavior of adhesives and single-point connections like spot welds and screws.
And how do they model the possibility of an internal short circuit happening within that jelly roll during a crash? That seems like the ultimate failure mode.
Again, the approach depends on the level of detail in the model. With those very detailed layer-by-layer models, they can try to directly simulate the deformation of the thin separator layers and identify potential points where anode and cathode might touch, causing a short circuit.
And the simpler models?
More simplified, macroscopic models often use criteria based on the overall amount of compression or deformation the jelly roll experiences. If the deformation exceeds a certain threshold, the model predicts a higher likelihood of an internal short.
It sounds like this whole field of using computer models to predict battery behavior in crashes is still a very active area of research and development.
It certainly is, but the progress they've made so far is very promising. The expectation is that these virtual testing methods will become a standard and indispensable tool in the vehicle development process, ultimately leading to the design of safer and more efficient electric vehicles.
Okay, let's move on to a topic that sounds a little more intense. Thermal runaway. In the context of a battery, what exactly is happening when that occurs?
Yeah, it's a term you hear a lot. Thermal runaway is essentially a rapid and uncontrolled increase in a battery cell's temperature.
Uncontrolled being the key word.
Absolutely. It happens when the heat being generated inside the cell, usually due to some failure or abuse condition, exceeds its ability to dissipate that heat to the surroundings. It's like a snowball effect. The hotter it gets, the faster the chemical reactions proceed, generating even more heat, leading to a very quick and potentially dangerous situation, like a chain reaction that, once started, feeds on itself.
And I can only imagine that this rapid increase in temperature can lead to some pretty dramatic consequences.
It certainly can.
Yeah.
Fire, explosion, venting of toxic or flammable gases. These are all potential outcomes. To really understand this phenomenon, researchers have designed highly specialized test setups.
Okay.
The notes describe one such setup with a heatable chamber, like a small oven, very precise temperature sensors, systems for collecting and analyzing any gases that are released, and, of course, crucial safety features like a fume hood to contain potentially hazardous materials.
So they're essentially putting batteries in a controlled environment and then intentionally pushing them to their limits to see what happens, safely, hopefully.
That's the basic idea, yes, under very controlled and safe conditions. The described testing method involves fully charging a battery cell, carefully preparing it by removing any outer packaging, and then attaching very sensitive temperature sensors, thermocouples, directly to the cell surface. This prepared cell is then placed inside the test chamber, often under a non-reactive gas atmosphere like argon, and heated at a constant rate while they meticulously record changes in temperature and pressure with very high-speed data acquisition systems.
What actually happens when a battery cell goes into thermal runaway in one of these controlled experiments? What does it look like in the data?
The notes detail a typical experiment with a common type of lithium-ion battery called an NMC cell nickel-manganese-cobalt.
Okay.
They observed an initial period of slow, gradual heating as the external heater does its work. But then, once a certain temperature threshold was crossed, the temperature started to skyrocket incredibly quickly.
How quickly?
In this particular case, the temperature jumped from around 220 degrees Celsius to almost 690 degrees Celsius in just a matter of seconds.
Wow. Seconds.
Yeah, it's incredibly rapid. This rapid temperature increase is accompanied by the release of gases from the cell, often with significant force, what they call venting. And then, after hitting that peak, the cell slowly begins to cool down after the runaway event has essentially consumed the available reactants.
Okay.
The researchers even noticed that some of the released gases condensed on the walls of the test chamber after things cooled down, indicating the release of volatile liquid electrolyte components as well.
That sounds quite dramatic and potentially hazardous, even in a lab. How do they analyze all this data to better understand the thermal runaway process itself?
One very useful tool they employ is called a rate diagram. This is a graph that plots the rate at which the temperature is changing degrees per second, say against the current temperature itself.
Okay, so how fast it's heating up versus how hot it is.
Exactly. This helps them visualize even subtle shifts in the battery's thermal behavior that might be hidden in a simple temperature versus time plot. For the NMC cell, they were able to identify 3 distinct phases using this diagram.
What were they?
First, a slow initial heating, pretty much following the external heat source. Then a phase of more rapid, quasi-exponential heating where the battery starts generating significant internal heat itself. And finally, the rapid thermal runaway phase itself, characterized by the cell venting gases and reaching its maximum temperature very quickly.
And they conducted these experiments on different types of battery chemistries, right? Like LFP as well. What were the key differences they observed?
Yes, they tested cells with LCO-NMC, lithium cobalt oxide mixed with NMC, pure NMC, and LFP, lithium iron phosphate chemistries. And what's really interesting is that each type exhibited its own unique thermal runaway characteristics. The high-energy LCO-NMC cells reached the highest maximum temperatures overall, often exceeding 800 degrees C. The NMC cells peaked at a slightly lower temperature, maybe around 700 C in their tests, and the LFP cells showed a less intense runaway event with a much more moderate peak temperature, perhaps only reaching 300-400 C.
So LFP is generally considered safer from a thermal perspective.
Generally, yes, it shows a less violent thermal runaway. There were also some variations within each chemistry type in their tests, which they believe might be due to slight differences in how quickly the pressure relief valve or rupture plate in each individual cell activated and allowed gases to vent. That venting itself can have a cooling effect.
So it's clear that different battery chemistries don't all behave the same way when they overheat. That seems like a critical insight.
Absolutely.
Yeah.
One size fits all definitely doesn't apply to battery safety. They observed distinct temperature profiles and rates of temperature increase for each cell chemistry. The LCO-NMC cells appeared to be the most susceptible to overheating, exhibiting the lowest temperatures for both the onset of significant self-heating and the rapid runaway itself.
Meaning they're more easily triggered?
Potentially, yes. In contrast, the LFP cells demonstrated a greater ability to withstand higher temperatures before undergoing thermal runaway. Their onset temperatures were significantly higher.
The notes also mentioned different venting events during these experiments. What did they observe in terms of gas release? Was it just one big puff?
Not always. For the metal oxide-based cells, LCO-NMC and NMC, they typically observe 2 distinct venting events. An initial slower release of gas, followed by a much more rapid and forceful release right as the thermal runaway really took off.
Okay, and LFP.
The LFP cell, on the other hand, showed only a small and relatively gradual release of gas in their tests. For the metal oxide cells, the majority of the gas was expelled very quickly, often in less than a second during that second event, whereas the gas release from the LFP cell was much more prolonged, lasting maybe around 30 seconds.
And what about the actual chemical makeup of the gases that were released? Did that vary depending on the type of battery cell?
Yes, the analysis of the released gases revealed unique compositions for each cell type. Across all of them, hydrogen H2 and carbon dioxide CO2 were major components.
Okay.
However, the metal oxide cells also produce significant amounts of carbon monoxide, CO, which is toxic, along with smaller quantities of other flammable hydrocarbons like methane, ethylene, and ethane.
And LFP gases.
The LFP cells produce less CO and fewer of those hydrocarbons compared to the metal oxide cells in these tests. It's worth noting that they didn't specifically measure for the presence of hydrofluoric acid, HF, in these particular experiments, which is another potential hazardous gas component.
So really understanding these thermal runaway characteristics, the temperatures, the timing of events, the amount and composition of the released gases is absolutely crucial for designing safer battery systems and developing appropriate safety measures.
Precisely. This kind of detailed data provides essential information for designing effective thermal management systems that can prevent overheating in the first place, for predicting the potential hazards if a failure does occur, and for developing strategies to mitigate those hazards, like designing safe venting paths and robust enclosures to protect vehicle occupants.
Moving on to our next topic, the notes discuss application-related battery modeling. It sounds like there are different levels of sophistication and complexity in these models depending on what you need them for.
That's right. Battery models are indispensable tools for describing and predicting how batteries will perform in real-world applications, like in an electric car. They can also significantly reduce the need for extensive and costly physical testing.
Saves time and money.
Exactly. These models can range from relatively simple ones, based on empirical observations, just curve-fitting data, basically, to very complex mechanistic models that try to simulate the underlying physical and chemical processes happening inside the battery in great detail.
So you choose the model complexity based on the job.
Pretty much. The key is to choose the right level of complexity for the specific purpose you have in mind. You don't always need the most complex model if a simpler one does the job well enough.
The notes mention something called equivalent circuit modeling, or RC models. What are those, and why are they a popular approach?
RC models. They're very common. They are based on the idea that, from an electrical perspective, a battery behaves somewhat like an electrical circuit containing resistors, or capacitors, C, especially when it's being charged or discharged in a dynamic way, like during acceleration or braking.
Okay.
These models use simplified electrical circuits made up of these R and C components, sometimes just one pair, sometimes several in series or parallel, to mimic the battery's voltage and current behavior.
And why are they popular?
They're often quite fast to compute, which makes them very useful for real-time applications like in a battery management system, BMS, running on a car's processor. However, they don't necessarily provide a deep understanding of the fundamental chemical processes happening inside the battery. They're more like a black box representation of the electrical behavior.
How do engineers actually determine the values for those virtual resistors and capacitors in these RC models? Where do the numbers come from?
One common technique is to use electrochemical impedance spectroscopy, or EIS.
EIS.
Yes. This involves sending a small alternating current signal through the battery over a range of different frequencies, from very high to very low, and measuring how the battery resists that current, its impedance, at each frequency.
Okay.
The resulting data can be plotted in a specific way called a Nyquist plot. The shape of this plot, often showing semicircles and lines, can be analyzed, and engineers can try to fit the parameters of an equivalent circuit model, the R and C values, so that the model's impedance response matches the measured EIS data.
So it's like using electrical signals to probe the battery's internal characteristics and then fitting a simplified circuit to that behavior.
In a way, yes. The semicircles you see in a Nyquist plot often correspond to different electrochemical processes within the battery, like charge transfer at the electrode surfaces or diffusion limitations, each with its own characteristic resistance and capacitance.
Yeah.
And the point where the plot intersects the horizontal axis at high frequency can often tell you about the purely ohmic resistance of the battery, things like electrolyte resistance, contact resistances.
The notes then move on to more fundamental electrochemical modeling. What are some of the key aspects that these more detailed models try to capture, going beyond just R's and C's?
Right. These are the physics-based models.
Mm-hmm.
At a fundamental level, a battery cell consists of two electrodes, a positive one, cathode, and a negative one, anode, separated by an electrolyte, which allows ions to move between them. Electrochemical reactions take place at the surfaces of these electrodes. These reactions convert the flow of electrons in the external circuit, what we measure as current, into the movement of ions, like lithium ions, within the electrolyte, and vice versa during charging and discharging. Each electrode has a characteristic equilibrium potential, and the difference between them is the cell's open circuit voltage. When you connect them externally, the cell can deliver electrical current as long as there are reactive materials available.
And what controls how fast these reactions happen?
The speed of these reactions, and thus the amount of current that flows, are influenced by factors like temperature, the concentration of reactants, and critically, the electrochemical potential difference at the electrode surfaces compared to their equilibrium potential. This difference is called the overpotential.
And how is the relationship between the current flow and this overpotential described in these models?
That relationship is often described by a famous equation called the Butler-Volmer equation.
Butler-Volmer.
Yes. Essentially, this equation helps engineers understand how the speed of the chemical reactions, the current density, relates to the overpotential. It takes into account things like the intrinsic speed of the reaction at equilibrium, known as the exchange current density, and how easily electrons can be transferred. It's a cornerstone of electrochemical kinetics modeling.
What about the movement of charged particles, like lithium ions, within the electrolyte? How is that modeled? That seems important, too.
Absolutely crucial. The transport of ions in the electrolyte is primarily driven by diffusion, the natural movement of ions from areas of high concentration to areas of low concentration. This process is described by the Nernst-Planck equation.
Nernst-Planck.
Right. This equation also accounts for the influence of the electric field on ion movement, which is called migration, and in some cases, the physical movement or flow of the electrolyte itself, called convection, although convection is generally limited in most battery designs. One potential issue that can arise, especially during fast charging at low temperatures when overpotentials are high, is the formation of dendrites. These are tiny finger-like structures of lithium metal that can grow from the anode through the separator and eventually cause an internal short circuit. Modeling the conditions that lead to dendrite formation is a key safety focus.
And the movement of electrons within the electrodes and the current collectors, that seems like it might be a bit more straightforward to model compared to ions swimming around.
Generally, yes. Electron transport within the solid parts of the battery, like the active electrode materials and the thin metal current collector foils, usually copper for the anode, aluminum for the cathode, is typically modeled using Ohm's law.
Just VIR.
Pretty much, relating the current to the electrical conductivity of the material and the electrical potential difference. However, even here, factors like the relatively low conductivity of some active electrode materials or the thinness of the current collectors needed to save weight and space can still contribute significantly to the overall internal resistance and heat generation of the battery.
The notes also mention the use of porous electrodes in many batteries. Why are they designed to be porous, and how does that affect the way they need to be modeled?
Good question. Porous electrodes are used to significantly increase the surface area where those crucial charge transfer reactions can take place between the solid electrode material and the liquid electrolyte.
More surface area equals more power.
Exactly. A larger surface area means more reactions can happen simultaneously, leading to higher power output and better overall performance, especially at high charge or discharge rates. However, this porous structure, which is like a sponge filled with electrolyte, also makes it more difficult for ions to move through the electrode material to reach reaction sites deep inside. The path is longer and more tortuous.
Ah, so it helps and hinders.
In a way, yes. The Bruggeman's relation is often used as an empirical way to estimate this reduction in the effective diffusion rate of ions and the effective electrical conductivity within these porous materials compared to their bulk and non-porous values. It accounts for the porosity and tortuosity.
Then there's the concept of ion intercalation, which is key to how lithium-ion batteries work, right? How is that different from other battery technologies, and how is it incorporated into these detailed models?
Yes, intercalation is fundamental to Li-ion. Unlike many older battery technologies where ions might simply plate onto or dissolve from the surface of an electrode, in lithium-ion batteries, the lithium ions actually move into and are stored within the crystal structure of specific host materials in the electrodes.
Like tiny parking garages for ions?
That's a great analogy. For example, graphite is the common parking garage material for the anode, and various metal oxides like NMC or LCO or phosphates like LFP are used for the cathode. When modeling this process, engineers consider how easily ions can enter the structure and how much the material's potential changes as it fills up with lithium.
Does it fill up evenly?
Not always. They often distinguish between what are called energy-controlled systems where all the parking spots tend to fill up in parallel, leading to a battery voltage that changes gradually and continuously with the state of charge, and entropy-controlled systems, like LFP often behaves, where the storage sites tend to fill sequentially, often resulting in a discharge curve that stays relatively flat over a large portion of the battery's capacity, making source estimation harder from voltage alone.
And of course, the thermal behavior of the battery is absolutely critical, as we discussed with thermal runaway. How do these more detailed electrochemical models account for heat generation and how that heat moves around?
Right, coupling the electrochemistry with thermal behavior is essential. Thermal modeling in these detailed electrochemical models primarily focuses on two key aspects. Heat conduction, which is how heat moves through the different materials of the battery, described by Fourier's law of heat conduction, and heat generation.
Where does the heat come from?
Heat is generated within the battery primarily from two sources. First, there's Joule heating, or resistive heating, which comes from the resistance to electron flow in the electrodes and current collectors, and resistance to ion flow in the electrolyte. Second, there's heat generated by the electrochemical reactions themselves, which can be either exothermic, releasing heat, or endothermic, absorbing heat, depending on the reaction and conditions. This reaction heat is often related to the overpotential and the entropy change of the reaction. These models then simulate how this generated heat is conducted through the various layers and eventually transferred to the surroundings, or how it might build up internally.
The notes also talk about something called homogenization when modeling the jelly roll structure inside cylindrical or prismatic cells. What's the idea behind that? It sounds like that macroscopic approach we touched on earlier.
Exactly. It's a way to implement that macroscopic approach mathematically.
Yeah.
Because the jelly roll structure, or electrode stack in prismatic cells, is made up of so many incredibly thin layers of different materials, anode, cathode, separator, repeated over and over, trying to model each individual layer in a simulation of a larger battery system, like a module or a pack, would be computationally prohibitive. Just too many elements.
Right.
Homogenization is a mathematical technique that allows engineers to essentially average out the properties of these different thin layers over a larger, more manageable virtual grid or volume element. This way, they can treat the jelly roll stack as if it were a continuous material with effective, direction-dependent thermal and electrical properties without having to explicitly model each individual separator, anode, and cathode layer.
How do they determine what these effective average properties should be?
It depends on the property and the direction. For thermal conductivity, for example, they consider how heat would flow both perpendicular to the layers through the stack and parallel to the layers along the winding. Heat flow perpendicular is often limited by the low conductivity of the separator, so the effective conductivity is calculated using something like the harmonic mean of the individual layer conductivities. Heat flow parallel is easier, more like conductivities in parallel, so they might use the arithmetic mean, weighted by layer thickness.
And for electrical properties?
For electrical behavior, it's a bit more complex. They often make assumptions about how the current flows, essentially perpendicular to the current collectors within the porous electrodes where the reactions happen. This allows them to derive an effective electrical conductivity for the homogenized domain, noting that the conductivity in the direction normal, perpendicular to the electrode layers, is effectively zero because of the insulating separators. They also have to carefully scale the current density from the microscopic level, current per reaction surface area, to the macroscopic level, current per volume of the homogenized cell, using factors like the specific surface area of the electrodes and the volume fractions.
It sounds like this homogenization technique is a clever, necessary simplification to bridge the gap between the very detailed microscopic behavior within a cell and the overall performance of a large battery system.
Exactly. It allows them to create a hierarchy of models with different levels of detail. They can use very detailed models to understand the fundamentals and parameterize the homogenized properties, and then use these computationally cheaper homogenized models to simulate entire battery modules and packs with a reasonable amount of computational effort, while still capturing the essential thermal and electrical behavior that originates at the cell level.
Our next section delves into the analytical methods used to investigate the aging of lithium-ion batteries. This seems absolutely critical for understanding how long these batteries will last in real-world applications, like EVs.
It is indeed. As lithium-ion batteries have become the dominant technology for portable energy storage and are poised to revolutionize transportation, understanding how and why they degrade over time, lose capacity, increase resistance is crucial for predicting lifespan, ensuring reliability, and developing strategies to make them last longer.
So how do they study this aging?
These aging investigations involve detailed comparisons of the chemical and physical characteristics of new, fresh battery materials with those that have been used and aged under various conditions. This can include looking at the raw materials themselves, freshly manufactured electrodes, cells that have gone through the initial formation process, where key protective layers form, and of course, cells that have been aged by repeated cycling or simply stored for long periods, perhaps at high temperatures.
And to do this properly, the researchers often need to design their experiments very carefully, right?
Yes, and I noticed the notes emphasize the importance of design of experiment, or DOE.
Why is DOE such a key part of studying battery aging? It seems like you could just cycle a battery until it dies.
You could, but battery aging is influenced by a whole host of interacting factors. How quickly you charge and discharge, C rate, the temperature it operates at, the voltage window you operate within, how deeply it's discharged in each cycle, depth of discharge, DOD, how long it sits at high states of charge. The list goes on.
Okay, lots of variables.
Right. DOE is a systematic, statistical approach to designing experiments that allows researchers to vary these different factors simultaneously in a controlled and efficient way. This helps them to isolate the effects of each factor and, importantly, understand how they might interact with each other to accelerate or mitigate the aging process. It ensures that the results they get are representative and can be used to build reliable, predictive models of battery lifespan under different usage patterns. It avoids just testing randomly.
Once they have these aged battery cells from their DOE tests, how do they actually get the materials out so they can perform all these detailed analyses? Sounds tricky.
It is. The process of taking apart a battery cell, sometimes called a post-mortem analysis or teardown to get to the internal components, is quite involved and potentially dangerous.
Yeah, I bet.
The first step is always to bring the cell to a completely discharged state, a safe state, to minimize any electrical hazards. Then the cell needs to be carefully opened. This must be done by trained personnel in a controlled environment, usually inside a glove box filled with inert gas like argon.
Why inert gas?
To prevent the highly reactive components inside, especially lithium metal deposits or the electrolyte, from reacting with air or moisture, which could alter the samples or even cause a fire. Safety precautions, like having liquid nitrogen available to quickly cool down the cell if it starts to unexpectedly heat up during opening, are essential.
Opening a battery sounds inherently risky. What are some of the specific challenges they face?
One of the main challenges is preventing an internal short circuit while you're trying to cut or pry the cell open. You could accidentally push the anode and cathode together.
Ah, yeah.
So it's absolutely crucial to know the internal design of the specific battery beforehand, where the different layers and components are located, to avoid accidentally puncturing the separator or connecting the positive and negative terminals. They use different techniques depending on the type of cell: cylindrical, prismatic hard case, or a pouch-type bag cell.
Are some easier than others?
Generally, pouch cells are the easiest to open inside a glove box, using non-conductive, non-reactive ceramic tools like scissors or knives to avoid any contamination or shorting. Hard-case prismatic cells often require specialized tools like miniature saws or mills, used very carefully inside the glove box, which introduces more risk of creating contaminating dust or debris during the opening process.
After they've managed to safely open the cell, how do they extract the electrolyte liquid for analysis? Soak it up.
Traditionally, various solvent extraction methods have been used, like soaking the components in a known solvent to dissolve the electrolyte salts and additives, then analyzing the resulting solution. However, a more recent and increasingly popular technique is using supercritical carbon dioxide, CCO2.
Supercritical CO2, like for decaf coffee.
Exactly like that, actually. In its supercritical state, CO2 acts as a solvent. This method has several advantages for electrolyte extraction. It's often faster, it can be more selective in what it extracts by tuning pressure and temperature, it's generally more efficient, and the CO2 simply evaporates away afterwards, often eliminating the need for the same level of pre-concentration or post-extraction cleanup that traditional solvent methods require.
And what about the solid electrode materials themselves? How do they take samples of those for analysis? Just scrape some off?
The way they sample the electrodes can depend on the size and design of the cell. For very small, lab-style coin cells, the entire electrode might be punched out and used for analysis. But for larger cells, especially those with long wound electrodes like in cylindrical cells, they might take samples from different locations, for example, punching small discs from near the current collector tabs, from the middle of the electrode length, and from the far end.
Why sample different locations? Does aging happen unevenly?
It often does, yes. Due to current distribution and temperature gradients within a large cell, aging effects like lithium plating or SEI growth might be more severe in certain areas than others. Spatially resolved sampling helps capture this inhomogeneity.
I noticed a note about sometimes needing to wash the electrode samples. Why would they do that, and are there any potential downsides to washing?
Right, washing. Electrode samples, after being removed from the cell, are often coated with residual electrolyte salts. Washing, usually with a solvent like dimethyl carbonate, DMC, is often necessary to remove these salts.
Why remove them?
This is particularly important if the sample needs to be transferred out of the inert atmosphere of the glove box for certain types of analysis, as these salts can react with air and moisture, potentially forming artifacts or interfering with the measurement.
Right.
However, the washing process itself can also have drawbacks.
Like washing away important stuff.
Exactly. It might unintentionally remove or alter the solid electrolyte interface, or SEI layer. The SEI is a very thin but incredibly important passivation layer that forms on the anode surface during the battery's initial cycles. It controls further electrolyte decomposition and is critical to the battery's long-term performance and aging. Aggressive washing could damage or dissolve parts of the SEI. So, researchers have to carefully consider whether washing is necessary, choose the solvent and procedure carefully, and be aware of the potential impact on their results.
The notes then go on to list a whole range of specific analytical methods. It looks like a chemistry lab's wish list. Can you give us a quick overview of some of the key techniques they use to investigate how electrodes age?
Absolutely. They use a really impressive array of techniques, often in combination, to get a comprehensive picture of what's happening at the electrode level as it ages.
Okay, hit me with some acronyms.
All right. X-ray diffraction, or XRD, is used to identify and quantify the different crystalline phases present in the active electrode materials. You can see if the crystal structure is changing or if new, unwanted phases are forming.
Okay, structure changes.
Scanning electron microscopy, or SEM, allows them to visualize the surface morphology of the electrodes at a microscopic level. They can look for changes in particle size, the formation of cracks in the particles, or the deposition of decomposition products on the surface.
Seeing the damage.
Transmission electron microscopy, or TEM, provides even higher resolution imaging down to the nanoscale. This allows them to study the internal structure of the electrode particles and, crucially, the interfaces, like imaging the structure and thickness of that SEI layer in great detail.
Really zooming in.
Then there's X-ray photoelectron spectroscopy, or XPS. This is used to analyze the chemical composition and the oxidation states of the elements right on the very surface of the electrodes, typically the top few nanometers. This provides valuable chemical information about the SEI layer's composition, although it is very sensitive to exposure to air, so samples usually need careful handling.
What else for surfaces?
Secondary ion mass spectrometry, or SIMS, is another surface-sensitive technique. It bombards the surface with ions and analyzes the ions ejected. It can provide elemental and molecular analysis of the surface and interfaces, and by sputtering away material layer by layer, it can create depth profiles to see how the composition changes as you go deeper into the SEI, or the electrode material.
Wow, okay. What about identifying molecules?
For that, you have techniques like Fourier transform infrared spectroscopy, or FTIR, and Raman spectroscopy. These use light to probe the vibrations of chemical bonds, allowing them to identify the different chemical functional groups present in the materials. This gives insights into the organic and inorganic components of the SEI layer and can also detect structural changes in the electrode materials themselves. For example, Raman is very good at looking at changes in the graphitic structure of the anode, like increasing disorder, which is linked to aging.
That's a lot of different ways to look at the electrodes. What about the other key components of the battery, like the electrolyte liquid and the separator membrane? How do they analyze those?
Good point, they age too. For the electrolyte, gas chromatography coupled with mass spectrometry, or GCMS, is a primary technique for separating and identifying the volatile organic compounds present, like the original solvents and any decomposition products. For elemental analysis, like looking for dissolved metals that might have leached from the cathode and deposited on the anode, a known aging mechanism, they use inductively coupled plasma techniques, either optical emission spectrometry, ICP-OES, or mass spectrometry, ICP-MS. These are very sensitive for measuring the concentration of different elements.
And the separator, the plastic bit in the middle.
Right. The separator membrane is crucial for preventing short circuits while allowing ion flow. Its properties can change with age too. Pores can get clogged. It can degrade mechanically. To assess this, they might measure the Gurley number, which is an indication of how easily air can pass through it. A higher Gurley number means lower permeability, which could indicate pore clogging.
Okay.
They also often calculate the McMullen number, Nm. This is based on measuring the electrical resistance of the separator when it's filled with electrolyte compared to the resistance of the electrolyte itself. It's considered a more accurate measure of the separator's effective transport properties related to its porosity and the tortuosity of the pore paths.
Tortuosity, twistiness.
Exactly how winding the path is for ions. Another technique is mercury intrusion porosimetry, which can directly measure the size distribution and total volume of the pores within the separator material.
And for understanding how the electrolyte liquid itself ages and degrades, it sounds like they need to use a combination of analytical methods as well, maybe more than for the solids.
Yes, absolutely. The electrolyte is a complex cocktail of solvents, salts, and additives, and its decomposition can produce a wide variety of new chemical species. No single technique can give you the full picture of electrolyte aging.
So multiple methods needed.
Definitely. They need to use multiple methods to detect and quantify the wide variety of ionic and organic compounds that might be present, as well as any elemental impurities. They often start by trying to understand the fundamental decomposition pathways of the conducting salt, like the common LiPF6 and the various organic carbonate solvents, like EC, DEC, EMC, and additives that make up the electrolyte.
How do they quantify all those breakdown products?
Techniques like GC and high-performance liquid chromatography, or HPLC, can be used to separate and quantify many of these organic compounds if they have matching chemical standards available to calibrate the measurement. However, it can be much more challenging to identify and quantify unknown decomposition products for which they don't have standards.
Yeah, that sounds hard.
In these cases, they might use more advanced techniques that couple separation methods like ion chromatography, IC, or liquid chromatography, LC, directly with mass spectrometry, using interfaces like electrospray ionization, ESI, giving methods like IC eSIMs or LC eSIMs. This helps identify unknown species by their mass. Getting quantitative information without standards is still tricky, but sometimes they can couple these separation techniques to elemental detectors like ICP-OES or ICP-MS to get quantitative information about specific elements within the separated compounds.
It really sounds like investigating battery aging is a very complex puzzle, a rapidly evolving field requiring the continuous development of new analytical techniques and maybe even the creation of new standard reference materials just to be able to compare results accurately between labs.
That's precisely right. To truly understand and predict the long-term performance and lifespan of lithium-ion batteries with the accuracy needed for widespread adoption in demanding applications like EVs, ongoing research into these advanced analytical methods, improving quantification, and developing robust standards are absolutely essential. It's a huge ongoing effort.
Our final technical section dives into something called Bayesian inference for lithium-ion cell parameter estimation. That sounds pretty advanced, maybe a bit statistical, but the goal is still to get more accurate computer models of batteries, right?
Exactly. The increasing demand for optimized lithium-ion batteries in everything from portable electronics to electric vehicles is driving the need for more accurate and predictive computer models, particularly those mechanistic models we discussed earlier that try to reflect the fundamental electrochemical processes happening inside the cells.
But you said those are complex.
They are. And because they're complex and often highly nonlinear, these detailed mechanistic models can be quite computationally demanding to simulate, and perhaps more importantly, challenging to invert, meaning figuring out the right values for all the model parameters, like diffusion coefficients, reaction rates, etc., based on experimental measurements. Traditional optimization methods might find a set of parameters that fit the data, but they don't really give us a good sense of how uncertain those parameter estimates might be, especially when we're dealing with real-world experimental data that always has some level of noise or error.
Okay, so traditional methods give you one answer, but maybe not the confidence level.
Exactly. That's where Bayesian methods offer a powerful statistical framework to address these challenges. They allow us to combine prior knowledge or beliefs about the parameters with the information contained in the experimental data to obtain a full probability distribution for each parameter, which inherently includes information about the uncertainty.
So it's a way to use statistical methods to estimate the key properties of a battery model, even when the model is complex and the data isn't perfect, and it tells you how confident you can be in those estimates.
That's a very good summary. It involves using Bayes' theorem. You start with a prior probability distribution representing your initial beliefs about the parameter values, maybe based on literature or previous experiments. Then you combine that with the likelihood function, which quantifies how likely your observed experimental data is given a particular set of parameter values. The result is the posterior probability distribution, which represents your updated beliefs about the parameters after considering the data. This posterior distribution contains all the information, including the most likely value and the uncertainty around it.
The notes mention something called parameter screening first. What's the point of doing that before trying to estimate the parameters using these Bayesian methods?
Right, parameter screening. With these detailed mechanistic models, there can be a large number of different parameters, sometimes dozens, that influence the battery's behavior. Trying to estimate all of them simultaneously can be computationally very expensive and statistically difficult, especially if some parameters have very little influence on the output you're measuring. Or some parameters are highly correlated, meaning if you change one, you can compensate by changing another, making it hard to tell them apart.
Okay, so weed out the unimportant ones first.
Essentially, yes. Parameter screening techniques, like the Morris one-at-a-time MO8 method mentioned in the notes, are used to systematically evaluate which of these parameters have the most significant impact on the model's predictions under the conditions you care about. This allows researchers to identify the subset of key parameters that really matter and focus their Bayesian estimation efforts on accurately estimating those, while perhaps fixing the less influential parameters to reasonable literature values. This can greatly simplify the overall parameter estimation problem and make the computation feasible.
And then they use these things called Markov chain Monte Carlo, or MCMC methods. That sounds complicated. What are those, and how do they help in estimating the battery parameters within this Bayesian framework?
MCMC methods are the computational workhorse for modern Bayesian inference, especially when dealing with complex nonlinear models, where you can't just calculate that posterior distribution directly using math formulas. MCMC methods are a class of sophisticated computer algorithms that allow us to draw samples from these complex probability distributions, like the posterior distribution of our battery model parameters. They work by constructing a sort of guided random walk through the high-dimensional space of possible parameter values.
A random walk?
Kind of. For each step in the chain, the algorithm proposes the new set of candidate parameter values, usually based on the current position. Then it decides whether to accept these new values and move there or stay put. The decision to accept is probabilistic, and based on how well the proposed parameters fit the data, the likelihood, and how plausible they are according to the prior distribution compared to the current parameters.
So it prefers steps that fit the data better.
Generally, yes. But it can sometimes accept steps that fit slightly worse, which allows it to explore the whole distribution and not just get stuck on the single best peak. Over many, many steps, the collection of accepted parameter values forms a chain that effectively gives us a large representative sample from the true posterior distribution.
So instead of finding a single best set of parameters, like traditional optimization might, MCMC gives you a whole cloud of likely parameter sets.
Exactly. And that cloud is the posterior distribution, represented by samples. This is where the power of Bayesian MCMC really shines because it automatically provides uncertainty quantification. By looking at the spread and shape of that cloud, or more formally, the histogram or distribution of the sampled values for each parameter, we can get a clear quantitative idea of how confident we are in our estimate of that parameter. A narrow distribution means high confidence. A wide distribution means lots of uncertainty.
Okay, that makes sense.
The notes describe applying MCMC in a few different test cases using a detailed electrochemical model, using simulated data without any added noise, a sanity check, using simulated data with realistic noise added, and even comparing the results of running multiple MCMC chains in parallel versus running just one long chain.
Why would they run these MCMC chains in parallel? Does that speed it up?
Not necessarily speed it up overall in terms of total computation, but running several independent MCMC chains simultaneously from different random starting points is good practice. It helps ensure that we're exploring the entire posterior probability distribution effectively and not missing anything.
How so?
It's possible, especially if the posterior distribution is complex with multiple peaks or weird shapes, for a single chain to get stuck exploring only one particular region of the parameter space. By running multiple chains, we increase the chances of discovering all the important features of the distribution and can check if they all converge to the same general result, which gives us more confidence.
The notes also mention a technique called early rejection that they use to speed up the computations. How does that work? Sounds useful if these models are slow.
Yes. Early rejection is a clever optimization strategy, particularly helpful when the forward simulation of the battery model itself is computationally expensive. Remember, during the MCMC sampling process, for each proposed set of parameter values, The computer model of the battery needs to be simulated to see how well its predictions match the experimental data that's needed to calculate the likelihood part of the acceptance probability.
Right.
If, very early on in that simulation run, say after just a few time steps, it becomes statistically clear that the model's predictions with these proposed parameters are going to be a very poor fit to the data, maybe the voltage is already way off, then the early rejection algorithm can abort the rest of that simulation step right there.
Doesn't finish the simulation.
No, it rejects those proposed parameters immediately without having to complete the entire potentially time-consuming simulation. This will lead to significant savings in computational time, especially for complex battery models that take a long time to simulate fully. The notes mentioned it reduced the workload by over 67% their case study.
Wow, that's a big saving. It sounds like Bayesian inference with MCMC is a really powerful set of tools for tackling the difficult problem of accurately estimating parameters in complex battery models, especially when you're dealing with the messy reality of noisy experimental data and need to know the uncertainty.
It is indeed, and the results presented in the notes strongly support its applicability for estimating dynamic battery properties and quantifying the uncertainties associated with those estimates. It gives you much more information than just a single-point estimate. However, the researchers also point out that further work is needed to more fully incorporate effects that are relatively constant or change very slowly over time, like capacity fade or resistance increase due to aging, within these dynamic MCMC estimation frameworks.
Our final section shifts focus slightly to data-driven methodologies, specifically for designing observers that can estimate a battery's state of charge, or SALI. Why is it so critical to have an accurate estimate of the SALI in, say, an EV?
Accurately, knowing the state of charge, essentially how much energy is currently stored in the battery, often expressed as a percentage, is absolutely fundamental for a well-functioning battery management system, or BMS.
Why is it so important?
Well, this information is crucial for safely operating the battery, preventing it from being overcharged or over-discharged, both of which can permanently damage it and shorten its lifespan. It's also essential for providing the driver with a reliable estimate of the vehicle's remaining range. Range anxiety is real, and it's needed for the overall energy management system, EMS, of the vehicle to make smart decisions about how to use the battery and, if it's a hybrid, the engine.
And we can't just measure SOCI directly.
Unfortunately, no. SOCI isn't something you can measure directly with a simple sensor like voltage or temperature. It has to be estimated or observed based on measurements we can make, like voltage, current, and temperature, using some kind of model or algorithm.
And this section focuses on approaches that are based on analyzing data from the battery, rather than relying solely on those complex electrochemical models we just discussed.
Yes, exactly. While physics-based models of batteries are very important and provide deep insights, data-driven methods offer a complementary approach. These methods learn the battery's behavior directly from experimental data without necessarily needing a detailed understanding of all the internal electrochemical processes.
When would you use a data-driven method?
They can be particularly useful when it's difficult or time-consuming to develop a completely accurate first principles model, or when you want a more general solution that could potentially be adapted to different battery chemistries or aging states more easily just by retraining with new data. They can also sometimes be computationally lighter for onboard implementation.
The notes mention a unified calibration workflow for people who might not be experts in battery modeling. What are the key steps in that kind of data-driven approach they describe?
This general workflow they propose typically involves three main stages. First, you need to design and conduct experiments to collect relevant data from the battery input signals and output measurements.
Step 1. Get good data.
Crucial. Second, you use that collected data to build a mathematical model of the battery's behavior through a process called nonlinear system identification. This is where the data-driven part really comes in. The model structure and parameters are learned from the data.
Step 2. Build the model from data.
Right. And finally, step 3. You use that identified model to design and analyze controllers, or observers in this case, an observer algorithm that can accurately estimate the battery's internal state of charge in real time using the available measurements.
It sounds like that initial experiment design is really critical for getting good results from a data-driven approach.
Well,
what are the key considerations when designing these experiments? You can't just use any data.
No, the quality and richness of the data are paramount. The primary goal of the experiment design is to subject the battery to a wide range of operating conditions, different charge and discharge current levels, varying temperatures, maybe dynamic current profiles that mimic real driving, so that the data you collect fully captures the battery's dynamic behavior and any important nonlinearities in its response.
Need to cover all the bases.
Exactly. You need to excite all the relevant dynamics and characteristics of the system sufficiently so that the identification algorithm can learn them properly from the data. You need enough data to train a reliable model, but you also want to minimize the testing time and cost. And of course, make sure you always stay within the safe operating limits of the battery during testing.
And for the actual data-driven battery modeling step 2, they mention using something called local model networks, or LMNs. What are those?
Local model networks are a type of flexible mathematical framework, a machine learning approach really, used for identifying and modeling nonlinear systems based on measured data. The core idea behind LMNs is quite intuitive. Instead of trying to find one single complex equation to describe the battery's behavior over its entire operating range, you break down that operating range defined by factors like current, temperature, maybe even SO itself, into several smaller, more manageable regions or regimes.
Okay, divide and conquer.
Exactly. Within each of these local regimes, a much simpler mathematical model, often just a linear model, is used to approximate the battery's behavior in that specific region. The overall output of the global LMN model is then calculated as a smooth, weighted combination of the outputs from all these individual local models. The weighting depends on how valid or relevant each local model is for the current operating point.
So it's like having a collection of simpler models that are each experts in a specific operating condition, and the LMN intelligently blends their predictions based on where the battery is currently operating.
That's a perfect way to put it. This approach allows you to capture the complex global nonlinear behavior of a battery quite effectively using a combination of simple or local models. LMNs also have the advantage that you can sometimes incorporate prior physical knowledge into the structure of the network or the form of the local models. And because the local models are often simple, the overall LMN can be computationally efficient, which is crucial for real-time applications within a BMS.
How are these local models and the boundaries between the regions of expertise actually determined in an LMN? Does the engineer decide, or does the data tell you?
It's typically learned from the data. The expertise or validity of each local model is determined by a validity function, often implemented using a structure that partitions the input space, the space defined by current, temperature, etc.
Yeah.
The notes mentioned using a logistic discriminant tree for this.
A tree structure?
Yes. This tree essentially learns the optimal boundaries that separate the different operating regimes based on the training data. At each split or node in the tree, a logistic sigmoid function is often used to create a smooth transition between the regions, determining the weighting for the corresponding local models. The parameters of these validity functions, defining the splits, and the parameters of the simple local models themselves are all learned simultaneously from the measured battery data using nonlinear optimization algorithms during a training phase.
So they essentially feed a bunch of experimental data into the LMN training algorithm, and it automatically learns the underlying input-output relationships and builds a model that can accurately predict, say, the battery's voltage based on current, temperature, and maybe C.
That's the core idea, yes. The LMN algorithm learns to partition the operating space and fit local models within those partitions to best match the training data. The notes actually show some impressive results where an LMN model trained on experimental data was able to accurately predict the battery's terminal voltage even for new, unseen validation data, demonstrating the model's ability to generalize well.
Okay, so step 2 gives us a data-driven model, the LMN. Now step 3, how do they actually use this LMN model to design an observer that can estimate the state of charge?
Right, the observer design. The LMN model, which is good at predicting the battery's terminal voltage based on current, temperature, and its estimated SO, is typically combined with another, simpler model that basically just keeps track of the battery's charge by integrating the current flowing in and out over time. This is sometimes called Coulomb counting, and it incorporates a Coulombic efficiency factor to account for losses.
So voltage prediction plus current integration.
Yes, but the Coulomb counting part can drift over time due to sensor errors or efficiency uncertainties. So the state of charge is estimated more robustly by using the LMN voltage model in a feedback loop. The algorithm compares the actual measured battery voltage with the voltage predicted by the LMN model using the current SOS estimate. Any difference or error between these two voltages indicates that the SOS estimate might be off, and this error signal is used to correct the SOS estimate, nudging it towards the true value over time. It's a closed-loop estimation scheme.
And what kind of specific observer structure do they typically use in conjunction with an LMN to implement this correction?
The notes mention a few different types of observers that can be adapted to work with LMNs, including the well-known extended Kalman filter, EKF. However, they go into more detail about the design of a fuzzy observer.
Fuzzy observer.
Yeah, it sounds a bit vague, but it's a specific technique. In this context, it leverages the local model structure of the LMN. The fuzzy observer approach involves representing the overall nonlinear battery system described by the LMN as a weighted combination of local linear state space models. The state of charge is included as one of the states in these models. They then adapt the standard Kalman filter equations, which are optimal for linear systems with noise, to work with this fuzzy, locally linear representation. Essentially, they compute a Kalman filter gain and update the state estimate, including SO, based on a weighted combination of the local linear models that are most active or valid for the current operating conditions.
And did this fuzzy observer approach demonstrate good performance in their tests for SO estimation?
Yes. The results they presented in the source material looked quite promising. They showed that the fuzzy observer, using the LMN model trained on data, was able to accurately estimate the battery's state of charge using validation data, even when the observer was started with the completely wrong initial guess for the SOS, like starting at 50% when the true value was 80%. The estimated SOS quickly converged to the correct value, demonstrating the effectiveness of this data-driven approach for robust, real-time SOS estimation.
So this whole section really emphasizes a practical, data-centric way to build battery models and SAW estimators, which could be incredibly valuable for implementing advanced and robust battery management systems in electric vehicles without needing extremely complex first principles models everywhere.
Exactly. It provides a systematic methodology to design experiments, identify a model from data, design an observer using that model that can potentially be applied more broadly, maybe even by engineers who aren't deep specialists in electrochemical modeling. And the results shown suggest it holds a lot of promise in terms of achieving both good model accuracy and precise state of charge estimation needed for real-world automotive applications.
Well, that was an incredibly comprehensive exploration of automotive battery technology. We really dug deep into a wide range of critical aspects today.
We certainly covered a lot of ground.
Yeah, from the fundamental principles of safety, ISO 26262 and all that, and the advanced techniques used for modeling battery behavior in various conditions, including those extreme crash and thermal runaway scenarios. Quite sobering stuff there. Then on to the sophisticated analytical methods needed for understanding how these batteries actually age and degrade over time. And finally, these cutting-edge data-driven and Bayesian approaches for accurately modeling batteries and keeping track of their state of charge.
It really highlights how multifaceted the challenge is.
It's so clear from all the information we've discussed that this is a field brimming with complexity, touching on everything from the tiniest electrochemical reactions within a single cell, like intercalation, all the way up to the fully integrated power systems within an electric vehicle.
And the interdisciplinary nature really stands out.
Absolutely. It's such an interdisciplinary endeavor, bringing together expertise from chemistry, materials science, mechanical and electrical engineering, and even the realms of statistics and computer science, like with the MCMC and LMN work.
You need all those perspectives to really tackle it effectively.
So considering the rapid advancements we've discussed across all these areas, modeling, safety, materials, analysis, it really makes you think. What future breakthroughs in battery technology do you believe will have the most profound impact in truly achieving the widespread and sustainable electrification of transportation as we move forward? What's the next really big leap we're waiting for?